Hi, my name is Stacy Simmons, and I'll be sharing how a crocheted hyperbolic plane helped me and maybe other students understand hyperbolic geometry. The two most common questions I was asked when I was working on my crocheted model was, "What are you making?" quickly followed by, "What is hyperbolic geometry?" One definition is that a hyperbolic geometry describes a surface with constant negative curvature. Well, what does that mean? Take a look at this picture that I took while visiting Glacier National Park. We can see curvature demonstrated well. Take a look at the peak on the right-hand side of the screen. If we were to traverse that peak from left to right, we would be crossing over a roughly positive type or outward curve. And the same would be true if we traversed any part of that peak from front to back. Gaussian curvature could be roughly described as the product of the two curves on these different axes. If we look towards the center of the picture, if we traversed from left to right, we would be following more of a negative curve, where if we went from front to back, we would be following along a positive curve. So at any point along this surface, the product of the two curves would be negative, otherwise having a negative Gaussian curvature. Sprinkles chips are also a common example when people look for surfaces with constant negative curvature. If I look at the first geometric figure, this is an example of negative curvature. The vertical lines have a negative curve, the horizontal lines have a positive, so at anywhere on this figure, the product of those curves would be negative. The middle has a zero Gaussian curvature because the vertical lines have no curve. The horizontal lines have a positive, so 0 times a positive curve at any point would result in zero curvature. And the last one, we have positive curvature in the vertical lines, positive curvature in the horizontal. Their product will always be positive no matter where we go. So basically, other than some geometric figures, we've seen that mountains and chips can have negative curvature. But is that enough for studying hyperbolic geometry? Well, there's more in nature that can be described by hyperbolic geometry, such as corals and sea slugs, otherwise known as nudibranches. Plants such as kale, lettuce, holly leaves grow in that ruffled negative curvature type style, and cacti can often also have hyperbolic geometry. We also see hyperbolic geometry in art. M.C. Escher's art, such as the circle limit 3, is a popular example of hyperbolic geometry in something called the disk model. There's also hyperbolic geometry in architecture, such as in this pavilion outside the art department of a university, in a crocheted coral reef on display in Latvia, or in this hyperbolic lampshade. In science and technology, scientists have recently found that hyperbolic geometry is helping them make sense of the human brain and the way it stores information. A study in 2020 showed that hyperbolic geometry has helped model human perception of odors. As you can see in these graphs, this middle curve here is the hyperbolic geometry versus this dashed curve, which represents the actual data they collected. This larger dashed line above is the 3D Euclidean model. So in each of these graphs, it becomes apparent that hyperbolic geometry is making more sense of the data than Euclidean geometry is. Hyperbolic geometry is also being explored as a way to map the internet and networks of information to expand capacity and efficiency. There are many exciting discoveries yet to be made, but in order to embark on the path of hyperbolic geometry, we should know a little bit about where it came from. Euclid is known as the father of geometry. After all, his book, The Elements, is the first geometry textbook and the most printed book in the world next to the Bible. No one ever questioned the common notions or axioms which are true for all areas of mathematics and not just geometry. His first 4 postulates are also considered affirmations of truth. They are simple and concise and easily observed. However, Euclid's 5th postulate caused some debate. What makes Euclid's fifth postulate so different? Well, let's take a look. Even before reading it, we can see it is much more complicated than the first four postulates and axioms. It states that if a straight line falling on two straight lines, so we have our two straight lines, G and H, and our transversal T falling on them, make the interior angles on the same side less than two right angles. So angle 1 and angle 2 are less than 180 degrees. Then the two straight lines, G and H, if produced indefinitely, will meet on that side on which the angles are less than the two right angles. His first 28 propositions were proved without Euclid's fifth postulate, which means it's probably true that Euclid began his work without the fifth postulate. Because so much of his work was able to be proved without it, many mathematicians spent over 2,000 years trying to prove that Euclid's fifth postulate was actually a proposition. Here are a few statements that mathematicians tried to use to replace or prove the fifth postulate. One of the most common equivalent statements is John Playfair's statement that through a given point can be drawn only one parallel to a given line. Playfair's axiom, as it is referred to, is often used as a replacement to Euclid's fifth in modern language. All of these statements, and many more, have only been successful in creating a logically equivalent statement to Euclid's fifth. Since all of these paths were not leading anywhere new, a few mathematicians decided to take a little different path. Giovanni Saccari, for example, constructed what is known as the Saccari quadrilateral. This quadrilateral has right angles at the base, at A and B, and equal legs, AB and BC. If C and D are right angles, then the base AB would be parallel to the summit DC, and Euclid's fifth postulate would hold true. So his goal, Saccari's goal, was to prove Euclid's fifth postulate using contradiction. If angles C and D are not right, they're either obtuse or acute. In his hypothesis of the obtuse angle, he assumed that C and D were obtuse angles, and he did eventually get to a contradiction. Although before he found that contradiction, he was able to prove that the base AB was greater than the summit CD, that the angle sum of a triangle always exceeds two right angles, and the angle inscribed in a semicircle is always obtuse. Since he succeeded in his contradiction here, he felt like he was well on his way. He moved on to the hypothesis of the acute angle, in which he supposed that angle C and angle D are acute angles. This time he showed many new statements to be true, but he was never actually able to truly come to a contradiction, although he thought he had. Some of the conclusions that he was able to come to included that in a quadrilateral, such as the one pictured, the base AB is less than the summit CD, that the angle sum of every triangle is less than two right angles, an angle inscribed in a semicircle is always acute, and that through any point not on a given line, there passes more than one parallel to the line. These are only a few of the conclusions he came to, but they paved the way for others to continue this line of reasoning. Building off the work of Saccari and others who took similar tracks, it is likely that Gauss was the first to discover hyperbolic geometry, which he is credited with naming non-Euclidean geometry. However, Gauss never published his work, in part because he didn't feel it was finished, and he never published anything he didn't feel was complete, and partly because he felt it was disrespectful to Euclid. I suspect he also knew that mathematicians at the time were not ready for these ideas. Janus Boye and Nikolai Ivanovich Lobachevsky also independently discovered hyperbolic geometry. In their work, Euclid's axioms, postulates 1 through 4 and propositions 1 through 28 held true. In a letter to Janos Boye's father, Gauss said, the assumption that the sum of three angles of a triangle is less than 180 degrees leads to a curious geometry, quite different from ours, the Euclidean, but thoroughly consistent. And that difference came about when they negated the fifth postulate, using Playfair's axiom instead of Euclid's original. When we do that, we get the hyperbolic parallel postulate, which states that through a given point, not on a given line, more than one line can be drawn not intersecting the given line. So if we take a point P not on this given line, then we can find infinitely many lines that are parallel or that not intersect our given line. This is often a picture that you might see illustrating this new postulate. I think for many it can be difficult to understand how this works or even imagine in what space this could be true, especially since the pages of a book and its illustrations often appear to follow the Euclidean geometry we learned in high school. This is why models can be helpful in illuminating concepts that are so difficult to imagine. This is particularly true if you don't even know what to imagine in the first place. There are quite a few examples of paper models created over the years. The first known model is a paper model by Eugenio Beltrami in the 1860s. Next to him is a picture of something called the pseudosphere, and from that paper pseudosphere, Beltrami cut a section of it to create this model, which is considered the first model of a hyperbolic plane. There are also, most notably, the paper annular model, the polyhedral model, and the hyperbolic soccer ball. The paper annular model is made by cutting annuli of the same radius, taping the inner edge of one annulus to the outer edge of another, and continuing this process until you've got a model the size that you wish. The polyhedral model is constructed by cutting out equilateral triangles. You then tape 7 triangles around every single vertex. In the hyperbolic soccer ball, you cut out regular heptagons and hexagons so that the side length of the heptagon is equal to the side length of the hexagon. You then tape a regular hexagon to each side of the regular heptagon. As you might imagine, these models can give you an idea of what a hyperbolic plane might look like, but they're not very durable. So folding them and handling them in general makes it difficult to use these models to truly experience the properties of hyperbolic geometry. Shade model comes in. Dana Tamina, a mathematician and artist in the medium of crochet, noticed that the paper annular model looked a lot like a row of crochet stitches. I followed her general directions that would allow you to create a hyperbolic plane of any size and any radius to come up with a crocheted hyperbolic model of my own. In the first model I made, I added a stitch in every third stitch. This led to a ruffling effect very quickly. I felt this would not be the easiest to use if I wanted to demonstrate properties of hyperbolic geometry, so I made a new one. In my new model, I added a stitch every 11 stitches. To create this model, you need to start with a slip knot that you can attach to your crochet hook. And then we need to create a chain of 20 stitches. We do this by yarning over, which is positioning the yarn so that the hook can pull the yarn through the loop. Once you've got your chain of 20, we start on our first row. We're going to create a stitch called a single crochet, starting in the second chain from the hook. A single crochet is made by inserting the hook into one of the previous chains, yarning over, pulling that through the chain, and then yarning over again to pull through the 2 loops that are on the hook. You continue this until you have 11 stitches. In the 11th stitch, you then insert the hook into the same stitch and add another stitch. Then you continue to single crochet until the end of the row. Once you get there, you're going to add a chain stitch before turning your work to start the process over again. In the second row, you repeat the same steps, adding another stitch in every 11th stitch as you go, until you get to the end of the row. Continue this pattern until you get a model as large as you'd like. When the model is as big as you want, you can stop by pulling the yarn through the last loop. As you can see, my model very much mimics the annular paper model, but I can fold it and handle it without worrying about it falling apart. Now that I have my new mathematical toy, it's time to play a little bit and figure out what kinds of new mathematics I might be able to understand. But in order to do that, it would be helpful to know a few rules and definitions, such as what makes a line straight. As Poincaré said, to ask what geometry it is proper to adopt is to ask, to what line it is proper to give the name straight. A line is often said to be the shortest distance between 2 points. We will refer to these lines as geodesics. If I fold my plane in half, as you might a piece of paper, I can highlight the folded line with a piece of brightly colored string. Folded as it is, it appears no different than a line drawn on a piece of paper. But when I open my model, you can see that the lines or geodesics do not behave in the way that lines do in Euclidean geometry. As you can see, these geodesics are curved. Geodesics are either radial or non-radial. The first example that you see on the screen now is a non-radial geodesic. We look at this next example. Here you can see 2 radial geodesics that cut across the annuli as if a radius is being extended through concentric circles. You can see that these radial geodesics are asymptotic as they approach infinity on one side and diverge on the other. What other properties of geodesics can we find? The first one is that every pair of points is joined by a unique geodesic. We've kind of already seen this property. So if I were to fold this, then the points I'm pinching would be the 2 points, and you can see that I have created a single line that's possible. You can also see that 2 geodesics intersect no more than once. So again, remembering that a geodesic is that shortest distance between 2 points. I've got my 2 geodesics. And as I look at my model, I can see that they are intersecting at 1 point. The next property states that every geodesic segment has a geodesic perpendicular bisector. So here I have my geodesic segment highlighted on my model and the line that I propose to be the perpendicular bisector. So if it's bisecting my line, I should be able to fold my segment along that line. And it should match up on each side, showing that the 2 halves are equal to each other, which it is. And if we take a look again at the way that these 2 lines cross, we can see that they do indeed appear to be perpendicular. We also should see that every angle between 2 geodesics has a geodesic angle bisector. So again, here's my first geodesic, or shortest distance between 2 points, and a second geodesic. And we can see that their point of intersection, we get some angles around them. So if I had a piece of paper, I could show that I have a bisector by folding it in half through the vertex. A little trickier with this model, but again, we're going to match up the 2 sides, fold it so that it's going through the vertex of those angles. So my fold here is where I have my geodesic, which is bisecting my angle. I have it highlighted here in yellow, and as you can see, my fold, those angles are lining on top of each other, or the sides of the angle. And as I unfold my model, it should be fairly easy to see that indeed I do have an angle bisector. The last one is that each non-radial geodesic is tangent to one annulus. And then, as you travel in both directions from that point of tangency, the geodesic approaches being perpendicular to the annuli that it crosses on the way to infinity. So here we have our non-radial geodesic, and highlighted in a light blue, you can see the annulus where that geodesic is tangent to it. As we move out to the ends, we can see that my non-radial geodesic is approaching a perpendicular or right angle to the annulus that it's crossing on its way to infinity. They're not quite there yet, but it's getting closer and closer to a perpendicular line. So let's revisit the hyperbolic parallel postulate. If you recall, this is the illustration that commonly appears in textbooks, but it really doesn't appear to support the postulate. So let's look at the situation when graphed on the crocheted model. Here I have a geodesic line that's given, and this point P here is not on it. If I fold along this line that's in the middle, this geodesic is clearly never going to intersect the given line, so it is parallel to it. But I can also fold along this geodesic going through the same point P, and I have another line that is never going to intersect the given. And here's a third. I can fold along this curve through the point P again, and I have another line that is parallel to my given. In fact, I could keep doing this as many times as I want. It becomes more clear in this model that we can find an infinite number of asymptotic parallel lines. Everything I've shown you so far has been very intuitive, but it's not necessarily very rigorous. In order to complete rigorous proofs, we will need to use Poincaré's half-plane model. But then, other than a few properties illustrated with this physical model, it would seem that the hours of time that it takes to crochet one of these things is barely worth it. But that won't be true if we can show that our crocheted model is the same as the upper half-plane model. In order to accomplish this, we'll need to define an intrinsic coordinate system on our model. So here we have our model, and we can let R be the fixed inner radius of an annuli. I'm going to let H sub delta represent the approximate annular hyperbolic plane that has a radius of R, and the thickness of the annuli would be equal to delta. If we choose an inner curve on any annulus on our hyperbolic plane, and we'll call this the base curve. So I have that base curve highlighted here. Next, we're going to choose a positive direction on this curve and a point on it to be the origin. Then we can construct our intrinsic coordinate system that we're going to call x sub delta, which takes our usual coordinate plane to our annular hyperbolic plane. So then, by definition, x is going to be the limit as the thickness of our annuli approaches 0 of x sub delta, mapping r squared onto h sub delta. So here we can see another point moving in a positive direction away from our point, our origin 0, 0, up to the point x of 0s. Now let's plot another radial geodesic. Keep in mind that the annuli all have the same radius, and that every time we cross an annulus, the distance between the radial geodesics change by rho divided by rho plus delta. So if we cross n annuli, the distance between two radial geodesics at some distance c, which we can define to be equal to n times delta, where remember delta is the thickness of any annulus, from the base curve. Then we have our formula d, which is some metric on r squared, times rho over rho plus delta to the n power. We can replace n with c over delta so that we have d times rho over rho plus delta to the c over delta. Now if we take the limit as delta goes to 0, then we have the distance between radial geodesics on this annular hyperbolic plane equal to d, our metric on r squared, times e to the negative c over rho. So we'd like to just recognize then that on the system, the coordinate map x preserves distances along the second coordinate curve. So if we travel from our origin at 0, 0 to this point at 0s, we have a length s. And it turns out then that this distance is the same if we go from this point w0 to ws. So that's what we mean when we say that it preserves distances along the second coordinate. The coordinate map x, though, does distort distances along the first coordinate. So if we go from 0, 0 to w0, you'll see that that distance is not preserved as we move along from 0s to ws. In fact, the distances along the first coordinate curve are distorted by a factor of e to the negative b over rho for some point x of AB. So by definition then, distortion would be if we let y represent a map from A to B, which is mapping one metric space to another, and let t, defined by lambda of t, be a curve in A. Then the distortion of y along lambda at that point p equal to lambda 0 is defined as the limit as x approaches 0 of the arc length along our curve lambda or y of lambda from y of lambda of x to y of lambda of 0 divided by the arc length along lambda from lambda x to lambda 0. Since we won't be able to have zero distortion in both coordinate directions, we will try to make the distortion in the second coordinate the same as the distortion in the first coordinate direction. So our goal is to find a change of coordinates that will distort these distances equally in both directions. This will allow our map to preserve angles. In other words, we would call our map conformal. It turns out that z of xy equal to our coordinate map x of x, comma, rho times the natural log of y over rho provides this desired change, with the domain of z being the upper half plane model and x as our geodesic coordinate map that we defined earlier. The following lemma will be useful to us in our quest to show that our crocheted model is the same as the upper half plane model. Before we take a look at the lemma, there are a few definitions I would like us to keep in mind. So here, just a reminder, rho is the radius of the annuli in our hyperbolic model. D times e to the negative c over rho, that's our distance between radial geodesics, where d is a metric from the usual coordinate plane. And then from the previous slide, we had said that the distortion that we needed, or the definition that we needed, was z of xy is equal to our coordinate map x of x coming from the x coordinate, and we're going to be replacing y with rho times the natural log of y over rho. All right, so the lemma. What we need is to show that the distortion of z along both coordinate curves that take x to z of xb and y to z of ay at the point z of ab is equal to rho over b. So to start the proof, let's let z of ab equal x, our coordinate map of A, and then remember, using that definition from the previous slide, we're replacing B with rho times the natural log of B over rho. Along the first coordinate curve, x is going to z of xb. So again, using that definition, we have x, our coordinate map, of x, then rho of the natural log of b over rho. And what we're looking at is the arc length from x of AC to x of XC, which if we refer back to this definition here for the distance between these radial geodesics, we are looking for the arc length between them. And using this formula, b, our usual metric, is the absolute value of the difference or distance between x and a times e to the negative c over rho. So if we use the definition of distortion, then what we're looking at is calculating the limit as x approaches a for the arc length between x of AC to x of XC divided by the distance from x to a. If we simplify this, we can divide out the absolute value of x minus a, which means that the limit as x approaches a is going to be equal to 1 over e to the rho times natural log of b over rho, all divided by rho. We can simplify that a little further, dividing out the rows. So we have 1 over e to the natural log of b over rho. Right? And since the exponential and base e and the natural log are inverses of each other, that leaves us with 1 over b over rho. That's really just the reciprocal. So what we have is rho over b as desired. Now we want to consider the second coordinate curve where y is going to z of ay, which, using our definition here, we're replacing y with rho times the natural log of y over rho. Along this coordinate curve, which is a radial geodesic, the speed is not constant. However, the second coordinate of x measures arc length, so the arc length from z of ay, which is equal to our intrinsic map x of a rho natural log of y over rho, to our point z of ab, which is equal to our intrinsic map x of a rho natural log of b over rho, is just going to be the absolute value of the difference in our y coordinates. And the distortion, by our definition of distortion, is going to be equal to the limit as y approaches b of the difference in our y coordinates divided by the absolute value of the difference in y and b. And since rho is the radius of an annuli and a positive value, we can factor out that rho from the numerator. And we can also take the absolute value of the limit as opposed to the limit of the absolute value in this case. But if you look inside the absolute value, that limit is just the definition of the derivative of our natural log of y over rho. And since we are evaluating this as y equals b, then what we end up with is that the derivative of the natural log of y over rho is just going to be equal to 1 over y. So we have rho times 1 over y, where y equals b. So again, we have our desired result, that the distortion is equal to rho over b. Now that we have proved the lemma, we need to define inversion with respect to a circle. We will show that inversion in a semicircle corresponds to a reflection isometry in the annular hyperbolic plane. An inversion with respect to a circle gamma is a transformation from the extended plane to itself that takes the center C from the circle to some point at infinity and vice versa, and that takes a point at a distance S from the center to a point on the same ray from the center that is at a distance of r squared over S from the center, where r is the radius of the circle. We call P prime an inversive pair, and the circle gamma is called the circle of inversion. Let's take a look at a few properties of inversions that will be helpful to us. Inversions are conformal, which means they preserve angle measures. So if you look at triangle CDE, the angles at C, D, and E are preserved by inversion to C prime, D prime. Inversions also take circles passing through the center of inversion to straight lines not through the center of inversion. So if you look at the circle that includes point F, you'll see that the inversion has taken that circle to the line that includes the point F prime. Inversions also take circles not passing through the center of inversion to circles. So if you look at the circle that includes the point G, that circle has been taken to the circle that includes the point G prime. So now we're ready to talk about the isometry of the upper half plane. If F is a transformation taking the upper half plane to itself, then consider this diagram where h squared is our hyperbolic plane, and we are mapping that onto the upper half plane in the same way that we think about mapping a globe onto a flat piece of paper. And then F is our transformation or the inversion through a circle that takes r squared plus or our upper half plane to itself. And then we're using Z, that map again, that's going to help us take our upper half plane back to our hyperbolic plane. Then our function G that we see taking the hyperbolic plane to itself can be defined as Z of F of Z inverse. And we can call our transformation F an isometry of the upper half plane model if the corresponding function G is an isometry of the annular hyperbolic plane. We're now ready to prove that G has distortion 1 at every point and is therefore an isometry. The theorem we'd like to prove is that let's let F be the inversion in a circle whose center is on the x-axis. Then the corresponding map G, which is equal to Z of F of Z inverse from our previous diagram, has distortion 1 at every point and is thus an isometry. Note that each of the maps, Z, Z inverse, and F, are conformal, in other words, they preserve angle measures, and has at each point a non-zero distortion that is the same for all curves at that point. Then, by the definition of distortion, we have that the distortion of G at P is equal to the distortion of Z of F of Z inverse at P. If you find the point P here on our first diagram, so P is on the hyperbolic plane, so that kind of curly figure is our hyperbolic model, then Z inverse would map P onto our point AB down here. So as we map to that new point, we are multiplying by some distortion factor. So that's going to be the distortion of Z inverse at P. Now we want to map the point AB using our map F onto F of AB. When we do that, we are multiplying by the distortion factor F of Z inverse at P. So we can multiply our distortion factor. And next we're going to map F of AB onto Z of F of AB. Again, multiplying by the distortion factor Z at F of Z inverse at P. So we can multiply those three distortion factors together. Our goal is to find each of the distortion factors for the product that we defined on the previous slide. So if we take a look at z of AB, this is defined to be the point P. Then the distortion of z inverse at P, well, if we kind of look at z inverse of P, that's mapping down here to this point AB on our diagram. And if we could reverse that map, we would be going through z instead of z inverse. And this is helpful because we proved a lemma that says that the distortion of z at AB is equal to rho over b, which is this part of our formula here. But if I move backwards through a mapping, then my distortion factor should be the reciprocal. So the distortion of z inverse at P should be equal to b over rho. That takes care of one part of the product. If we focus on this part of the picture in the lower left-hand corner, we are going to define our inversion F on the center, using the center of the circle C with this radius R. And we want to let this distance S from the center to AB, or this distance from C to AB be the distance S. And remember, AB is the same as saying Z inverse of P. Because inversions are conformal, as we discussed earlier, then the distortion is the same in all directions. So we really only need to check the distortion along this ray from the center of the circle C through the point P. Thus, the distortion of F at AB is equal to R squared over S squared by definition. This is going back to our definition of distortion earlier on, where we had said that if we could take the limit as x approaches 0 for the length of the arc from 0 to our point, divided by the length of the arc in another geometry or another set, then we would have our distortion factor. So the length from our center circle to f of AB by definition of inversion is r squared over s, and the length of the arc from C to the point AB is s, so r squared over s divided by s is s squared. We know that the distortion z at f of z inverse of P is equal to rho over c by our lemma, where c is the y-coordinate of f of z inverse of P. But if we look at the picture, f of z inverse of P is just the point f of AB. So to determine the y value of this point, we need to find this distance c. By similar triangles, we can show that in the original figure, right, the ratio of S to B should be equal to, if we look at our larger triangle, the ratio of R squared over S over C. We can solve this so that C is equal to B times R squared over S squared. And if we plug this value in for C in our previous definition or previous distortion factor, then what we have is the distortion of z at f of z inverse of P equal to rho times s squared over b times r squared after simplifying. Remember, at the beginning of the proof, we had defined the distortion of g at P to be equal to our distortion of z at f of z inverse of P times the distortion of f at z inverse of P times the distortion of z inverse at P. We have just found these three values in our proof, highlighted here, here, and here. If we put this all together, plugging into this formula, we have the distortion of g at P equal to 1 after simplifying. Now that we have shown that the annular hyperbolic plane is isometric or the same as the upper half plane model of the hyperbolic plane, all of the analysis techniques that have been developed for the upper half plane model can now be used for our annular hyperbolic plane model that we've crocheted. We have seen that this physical model can make the abstract ideas of hyperbolic geometry concrete and aid in the understanding of mathematics that's often difficult for people to grasp. So that brings us back to crocheting mathematics. We've seen how the annular hyperbolic plane can help aid in the understanding of this geometry that we're not usually exposed to until college. But what about the pseudosphere? Or maybe some knot theory like Brownian length? Or some more topics in topology like the Klein bottle or a Lorentz manifold? It leaves me wondering what other mathematical concepts could become more accessible by using crocheted models. Thank you for listening to my presentation. Have a great day.